Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. A while ago, I reviewed the Rohde & Schwarz ZNLE, which is a network analyzer here on the left side, but there is now a ZNL series, and this is a full network analyzer, spectrum analyzer hybrid, along with a bunch of other new functions. It's in the same form factor, which is quite nice, and I'm eager to put this to the test. There's a lot to do and to talk about, so let's get started. And here is the Rohde & Schwarz ZNL6, and in fact it looks identical to the ZNLE series, but it can do a lot more. This is a true 3-in-1 instrument, as we will see during our testing, and it still has the same tiny footprint. It's only 9.2 inches deep, and it fits on your bench very well. In fact, it has become my favorite portable network analyzer, spectrum analyzer hybrid because of its size and capabilities. In the front, we have the same 10.1-inch LCD screen. This is 1280 by 800 resolution, capacitive multi-touch, and yes, it is still just as reflective, and you can put a screen protector on there to help with some of that reflection. The button layout in this instrument is particularly important because it can jump back and forth between different modes of operation, spectrum analyzer, network analyzer. These buttons are essentially multifunction, and I think they've done a very good job. I do enjoy using this instrument with a mouse quite a bit. I don't really use the touch screen that much, but it is optimized to be used for both. On the left, we have the mode button, which is, of course, changing the different modes. The keyboard button is there, which is a really good addition, I think. And, it's quite usable and good choices over here. On the left, we have two USB ports, soft power button. In the back, there is a hard power button as well. And as I mentioned, all the different settings of different functions are also built here on the right. We do have a rotation knob. It is indeed selectable, which is good. And if you look at the frequency range over here, this can go from 5 kilohertz to 6 gigahertz. This is a fully configured instrument with all the options, and the ZNLE could only go down to 1 megahertz. And that difference makes a really big difference in some of the other applications. If you're looking at broadband amplifiers or some backplane and you want to make sure that you have a good connection at low frequencies, or if you're measuring passives and you want to make sure they don't resonate for, let's say, power supply decoupling and so on, being able to go down to 5 kilohertz is quite important. And for the ports, port 1 and port 2, remember this is a full 2-port network analyzer. They can take up to 27 dBm and 30 volt DC, which is also great. And we have the port 2 for the RF input. This instrument still has better than 120 dB of dynamic range, which is again excellent for an instrument in this class, all the way up to 6 gigahertz. And the design of it is clearly made for being field use and portable. These two little bumpers on the side prevent the screen and the connectors from hitting the ground if you put it upside down, and then we have the same thing at the back. Really, they have thought about making sure that this will survive, and there's a carrying case and bag for it too if you're interested in using it that way. Now, I have two versions of this. I have one that's slightly configured differently. A lot of the options in these instruments can be installed after you've purchased it, especially the software ones, of course, but there are some other configurations in the back that I do want to show you. So let's take a look at that. And here's the back of the Rohde & Schwarz ZNL6, and this particular unit is equipped with some of the really important interfaces that I think this instrument definitely needs. So we have the standard PC interface. This is a DVI port. There is no VGA or HDMI, but I think you can convert that. LAN and two USB 3.0s, and there are, of course, two USBs in the front as well. We have the power input, fuse, and hard power switch. This is a full voltage range covering North America and Europe at the same time. And this is the card that I'm really most interested in because it gives you power sensor interface as well as noise source control interface, which means that if you want to do noise figure measurements or do some precise power measurements, you need this option. It has to be purchased separately, but you can also purchase it later and add the card. And with the appropriate software, then you get all those functions. We also have the reference input, reference output, and trigger. This instrument can have an OCXO, but this particular unit doesn't have it. And you can see there are some blanks. I'll show you a different instrument that has those populated for different purposes. You can have all of them at the same time, which makes me really want to see the inside of this unit because it must be quite a bit of an engineering to fit all of this and be able to have them interchanged and removed and put back. I think there's some beautiful Rohde & Schwarz engineering inside this, which we'll take a look at. And here is a slightly different configuration of the ZNL6, and you can clearly see that this one has the lithium-ion battery option, as well as the external 12-volt power supply. This also has the GPIB interface for legacy support, but this unit can be powered from 3 different sources. And the nice thing is that these lithium-ion batteries are hot swappable, so if the instrument is running from an external power supply, you can simply remove any of these batteries anytime you want, and there is also an indication in the back of how much battery is left inside each of the 2 batteries in here. And once you plug them in, if you have an external power, they'll just simply charge the battery, making it quite easy to use. And the 12-volt power supply here means that you can power it from your car. Really, you can plug it in, have it charged, or just have a cable to the cigarette lighter, for example. And I think they've really thought about making this as portable as possible. But remember, all of this has to fit in this. So let's go ahead and take this apart and see how they managed to connect all these different options, as well as the RF deck and the motherboard and all the controls in the same chassis with different orientations. There are a lot of nice Rohde & Schwarz engineering that I'm eager to see in here. And here's inside this instrument. On the right side, we have a fairly large fan, and it is therefore very, very quiet. The instrument is essentially silent, sitting on your desk. Let's go ahead and remove these two batteries so we can see what's on the other side, and we should be able to see the main power supply and also how it interfaces to the main motherboard. So if you look over here, the main motherboard over here has a lot of different connections, and they all connect vertically to all these different cards that can come down into it. Here's the main power supply, and here's our 12 volts, which interfaces with the main power supply. So there's some automatic switching going on in there to ensure that the instrument is powered from the correct source. Let me go ahead and remove this GPIB card so we can take a look behind there. There we go, and that reveals our OCXO sitting right there. It's quite a little tiny board, and it's screwed here to the side, so you can of course replace this and change it. And I believe if you don't have that option, it probably uses some other 10 megahertz reference. This instrument also has a lot of machine aluminum pieces, so the batteries go into a cavity here, which is a totally custom part, and that gives the instrument a certain structural integrity, because again, these batteries are pretty heavy. You want to make sure they're well protected. A lot of effort's gone into it. We have custom aluminum pieces top and the bottom so that these don't become loose inside the unit. A lot of effort indeed has been put into this. Let's go and turn this a little bit so we can see on the side the various cards that go in. And if I completely turn it, we will eventually see the main RF deck. Now, this particular unit does not have the 40 megahertz option. I don't believe it does, but you can see the main RF deck over here. There's another empty part here. That could be the 40 megahertz option. Potentially could be another board that sits in here. Maybe there's some kind of a loopback or some kind of a connection between the other board. I'm not quite sure, but there's only two connections going into this. That's the two ports. So all the RF functions of this particular instrument, network analyzers, spectrum analyzers, all built into this. So I'm really curious to see what's going on. I think we should open this and take a look at it. And look at the little PC board. It's absolutely tiny. It has an SSD, the RAM, and the processor all in one, and of course the battery for the BIOS. Yeah, quite amazing. All custom made. So let's go ahead and take a look at this RF port of the ZN-L6, and look how beautiful it is. Look how compact it is. There are a lot of functions on this board in a very small area, and there is even components on the other side. Now, there is no block diagram, so we're going to have to see if we can do a bit of reverse engineering ourselves, and hopefully we'll get this right. So here's port 1 and port 2, and you can see a certain degree of symmetry between the two ports. That's not surprising, because this is a full 2-port network analyzer, and therefore it has to have some hardware replication on both of these ports. There's another port here called SPA. It doesn't seem to be connected to anything, perhaps some option that this particular unit doesn't have. I also don't think that this board is capable of the 40 megahertz analysis, as we will see later. Why not? So in the very front of port 1 and port 2, we seem to have some couplers, and these appear to be resistive couplers, and I've talked about these type of couplers in network analyzers before. By doing a vector measurement across a bridge in the appropriate places, when you have a stimulus signal, you can actually figure out the exact impedance connected to each of these ports. And of course, from that, you can extract the network analyzer as parameters after doing some calibration. So I think that's what's going on over here. So let's take the signal going into the instrument. So we come over here after the couplers, we have two paths. On one path, we have a digital attenuator. On the other path, we go straight in, and you can see some black diodes over here, 3 of them in series, and these are probably for clamping. And if you look carefully, you can see that there's some tricks played on the transmission lines in order to absorb the capacitance of those lines and create a uniform attenuation across frequency. This is a common technique as well. So if you look over here, we have 2 more amplifiers. These appear to be gas amplifiers, about 13 dB of gain each. We have 2 more over here. And then we hit a pair of mixers. These mixers work all the way up to 6 gigahertz, which is of course the maximum frequency of this instrument as well. And they have differential IF outputs. So those differential IF outputs, I believe, go into a set of filters on the other side of the board. They appear to be all passive. And I think they make their way towards these two ADCs. These are 10 megasample per second, 16-bit ADCs. They only have a bandwidth of about a few megahertz. That's why I don't think this instrument can do the 40 megahertz analysis. And you can see that there's 2 of them here for these 2 mixers, 2 more over here for these 2 mixers. I believe that's where the connection is made. So these 4 mixers are also going to need some LO signal. And therefore, we will need a synthesizer to produce that LO, and that synthesizer is right over here. The output of this synthesizer, which is also a 6 GHz synthesizer with built-in VCO, comes through a series of switches here, which allows it to be switched in and out of these connectors, which is interesting because these connectors don't seem to be accessible from inside the unit. They could be for factory testing or some other type of function that I can't quite figure out in this unit. But anyway, you can have a straight path after these solid-state switches. That straight path goes over here. You can see it splits into two using a resistive splitter and then gets amplified, so on, and eventually reaches two identically symmetric points, reaching into these four mixers. So the LO path of these mixers is, fairly well known. There's also some additional signal that comes through, which is interesting. There's some parallel path, but it's not a high frequency path. So I wonder what they're doing with that. There's a lot of stuff going on here. There's quite a bit of subtlety in the design of this. So anyway, so that's the LO of these four down-convert mixers over here. So now we have to figure out where the stimulus signal is generated. The stimulus signal has to be fairly pure, and it has to reach these two ports in exactly the same way. There's another synthesizer right over here. It goes out from here into a bunch of switches. Now these switches all have different filter banks. And by switching between these different filter banks, you can then isolate and eliminate all the other harmonics that you don't want. They could be subharmonic, they could be other multiplication factors coming from the synthesizer. They all seem to be filtered using this. There's even more of them on the other side. So the signal here and the signal here are identical, except the signal over here is filtered and quite a bit spectrally pure. All of these other ICs that you see are solid-state switches. And then we go over some amplification, some more digital attenuation, amplifier, and then we have a splitter here, or a switch probably switching back and forth depending on which port has the stimulus. So the signal goes over here, a bunch more amplification. We have a bow tie stop filters in there going back over here, and then we have two Rohde & Schwarz branded ICs, followed by two digital attenuators, two more amplifiers, and then ultimately going back into the bridge and making its way to the output. So this is a very rough kind of operation here, but there is even more stuff on the other side, which gives me a bit of a puzzle. I have to really think about the details if I want to figure out how it works. So therefore, we have an LO path going this way, or I should say the stimulus paths going all the way through these, all the way out here, and then the reverse path. So both of these synthesizers are going to need some kind of a reference, and I believe the reference for them are generated using these two ICs here. These are digital direct synthesis ICs, I believe up to 2.7 gigahertz, and they produce the necessary reference signal, I think, for these guys, and you have very agile tuning as a result of that. This is also a common technique. I've seen that done quite often, where you generate a certain reference or maybe even mix it with the synthesizer, but either way, this IC, this one, and this one are all involved in the generation of these signals. There's also a DAC here. I'm not quite sure what it is for. It doesn't seem to be connected to anything that I can recognize, but it's capable of producing a couple of hundred megahertz of signal. It could be that this is necessary to produce the really low frequency signals, because these synthesizers do not go down to DC. They go only about 27 to 30 megahertz. Perhaps that's what that is used for. So let's flip this to the other side, because there's something else I wanted to show you. So on this side we have, you can see these are all the LC filters that I believe are part of the IF path. And if you look over here, we have four other ICs, and these are ADC drivers. Now, I don't believe they're connected to ADCs. They could be using these for the low frequency path, producing the very, very low frequency sub 30 megahertz down to 5 kilohertz in the stimulus. Anyway, that's at least my guess. Hopefully someone else might be able to comment on this, or maybe even Rohde & Schwarz will drop us a comment here to figure out exactly if that is correct. Either way, I have to say, really impressed with the design of these boards. I've never opened a Rohde & Schwarz instrument where I've thought that the design was, not quite beautiful, really well thought out. That's to be expected. And here is our ZN-L6 in the test setup. When I did the review of the ZN-LE, I went into a lot of the GUI functions and how the software works. So I'm not going to spend so much time on that. Instead, we're going to jump directly into our experiments. For the ZN-L6, I have prepared an extensive setup where we can switch between the different modes of operation of the ZN-L6 without changing our setups. There's a lot of microwave switches and different components simultaneously connected to the two ports of this instrument. This is a kind of setup you would have, for example, during some automated testing or some factory testing, taking advantage of the multifunctionality of the ZN-L6. And here is our test setup. It looks pretty complicated, and that's because this is a fully configurable 2.4 GHz ISM band transmitter with up converters and various components to be able to test the ZN-L in different corners. Now, we have a couple of microwave switches in strategic places, this allows us to reconfigure this without actually taking anything apart and route the appropriate signal into the different ports of the ZNL when it's operating in different functions. So let's take a look and see what's going on. Here at the heart of this setup, we have a power amplifier, low noise amplifier hybrid. This is a bidirectional amplifier typically used in Wi-Fi systems, allowing you to use it as a transmitter up to 33 dBm, that's a lot of power, or in reverse as an LNA. Now at the output of this, I have two 10 dB attenuators. This is to protect the instrument because this puts out so much power. And then over here we have one microwave switch and another microwave switch. Both of them have their port 2 connected to the two ports of the ZNL. It means that the ZNL can actually inject the signal in this way and use this path to measure the S parameter in forward or in reverse, characterizing this PA LNA in both directions without changing anything. But at the same time, when I want to use the ZNL in a spectrum analyzer mode, I can change these switches and allow the signal to come from various other components into this power amplifier. So that's where things get even more interesting. We have a signal coming over here. This is coming from another synthesizer, which I will show you in a second. It means we can route this signal through this port 3 into the power amplifier and back into the ZNL, allowing us to test the power amplifier with a known LO signal directly at the input, or we can do a modulation on this and test the power amplifier with a known modulated signal. We can take that even a step further and switch this to the other side, allowing the signal of this to be used for the LO of an up converter, which is using IF at its input. So basically we have multiple layers of measurement. We can start from IF, do an up conversion, going to the PA. We can directly come with an RF modulated signal and then go to the PA, or we can just measure the PA by itself. And in reverse, we can use the LNA measurement. At the same time, we can reroute the output of this PA into a power sensor. And this power sensor is also connected to the ZNL, allowing you to measure the precise total power of this device over here directly using this power sensor. So this is a pretty configurable setup, allowing us to do a lot of different measurements. So let me show you all the equipment involved. Of course, we have over here the ZNL, of course, and then we have the Agilent 11713C. This is going to be controlling the microwave switches that allow us to reconfigure everything. On the left over here, we have a Rohde & Schwarz SMB100A. This allows us to provide an LO signal or allows us to provide a modulated signal to test the PA. And at the bottom, we have a Rohde & Schwarz AFQ100A, which is providing our I and Q differential signals into the up converter. So we have LO and RF, we have IF, we have the switch controller, and we also, of course, have the Rohde & Schwarz power supply, NGB800, which is a fantastic power supply that's providing power both to their PA as well as the up converter. And we can monitor the power consumption of the PA as it is pushed further and further into compression and see what kind of behavior we get from that. So a lot of measurements to do here. What's nice is that this entire setup is essentially in a Rohde & Schwarz ecosystem. We're using all Rohde & Schwarz components except for the Agilent 11713, which is the microwave controller. So let's go ahead now and take a look at the screen of the ZNL and do various measurements. So the first thing we want to measure is the S parameters of this PA-LNA hybrid. Now this is a tricky device to measure because it is bidirectional and it has a switch inside that automatically switches from LNA to PA depending on if there is enough power present at this port. By default it's in LNA mode, so the signal flows in this direction, and then when there's enough power here, it will turn into a PA mode and it will transmit in that direction. So let me go ahead and turn it on. There you go. You can see the red light is on, which means it is in LNA mode, and when the green light turns on, it is in PA mode. Now, I've already shown you in the ZNL-E that you can use the built-in S parameter calibration wizard and use an eCal module like this one. This is a ZN-Z151, which is an 8.5 GHz calibration unit, and it will walk you through all of the calibration, and it's quite easy and straightforward to use. That's a nice feature that they have built into the software. Now what we're going to do is we're going to basically calibrate to this point and this point in the system, bringing the measurement planes, including all the cables and microwave switches, so we can measure the S parameter of this module by itself, including the attenuators. Okay, so here we have the screen of the ZNL. At the bottom right, you have a live view of the setup. You can see that the eCal is connected to the two microwave switches. Let's go and perform a very basic auto calibration, which uses the instrument's existing settings to do a calibration. Here we go. Now I click on that. Now right away I get two errors. The first error is that the port 1 is missing. It means that the electronic calibration unit is detecting that there is no power coming from port 1 of the instrument. This is a very, very handy error to get because it tells me that the microwave switches are misconfigured and port 1 isn't actually being routed to the calibration unit. This is a very good function here. The second one is that the frequency range is out of the range of the electronic calibration unit as well. That one's an easy one to fix. Okay, so let's go ahead and fix those things. The very first thing, we can go ahead and reach the frequency over here and then change that to 1 megahertz. We don't need to work that low frequency anyway. You can see that's already changed to 1 megahertz. I'm going to also go ahead and reconfigure the calibration, the microwave switches, so we can reach the calibration unit. There we go. I just did that. And let's go ahead under the calibration menu one more time and perform an AutoCal. And you can see both of those errors are now gone and the calibration can be successfully performed. Once this is done, the instrument has the calibration is at exactly the planes of the eCal unit, and I can go ahead and reconnect them back to the power amplifier. Okay, so the electronic calibration unit has been replaced with a PA. You can see the PA in the setup right now, and we're measuring S21. Now look at the value of this S21. It's at below minus 50, about minus 55 dB. Now keep in mind that there is a 20 dB attenuation added to the output of this device under test. Now we could measure that separately and then de-embed it from the S parameters. For simplicity, let's just do it in our head. But this means that the gain of this amplifier from the left to the right side is quite low, even with a 20 dB attenuation. This obviously tells us that this bidirectional amplifier is not operating in a power amplifier, it's operating in an LNA mode, which means the signal is primarily supposed to flow from the right to the left. So let's add a trace to this so we can see that behavior. We can go under the trace. I'm going to add a trace diagram. It's going to give us a replication here. I'm going to change that from S21 to S12. And take a look. That now makes much more sense. So it's sitting at minus 10. It means that we're going to add 20 dB to this, so it has about 10 dB of gain when it's operating in LNA mode. Now keep in mind that this is supposed to sit in front of a router, which has its own LNA, so it doesn't have a lot of gain. Otherwise, you would totally compress the LNA inside the Wi-Fi, let's say, router that you have. So we have about 20 dB of gain in one direction, and we have about, let's say, minus 55, add 20 dB to that, about 30 dB of loss in the other. Now you can see there's a shape in there, even in the reverse path. This tells me that the power amplifier isn't actually turned off, but the switches in the front end are switched. And that makes sense too, because if you turn the power amplifier off, it's going to take a long time to turn the entire PA on and off. And that's why they don't do that. They keep the PA in standby and only use the switch to turn it. Now, can we investigate this behavior further and convince ourselves that we can indeed activate the PA by playing with the power at the input of this device? There's also an unusual behavior over here. It's at minus 35 dB or so, but it seems to have a second kind of peak here, which is a bit unusual, something inside the design of this module. Let's put a marker on this just so that we can see where that frequency is happening. Here's a marker. There we go. Let's grab the marker and put it over here. Around 2.4 gigahertz, right within the ISM band. That's to be expected. This is a Wi-Fi module after all. So let's go under power settings over here. Here's power. You can see that the incident power is minus 10 dBm. Now in this instrument, I cannot go below minus 10 dBm. You can configure it down to minus 40 with the appropriate option, and that would be useful if you're going to measure devices that have a very high gain or a very poor input compression, and that way you can still measure them. I don't have that option, but we can increase the power. Let's go from minus 10 to minus 5 and see what happens. Check this out. This is an interesting behavior again. So we still have the forward path gain, but at some point you can see that the reverse path, the gain picks up quite a lot. You see it at minus 10 again, which would then put us into the minus 20 range, plus 10 gain again, which means that at some point this is switching to PA mode because there is enough power at the input of this circuit to turn the PA on and enable the power to be transmitted in the opposite direction. That's how this is supposed to behave, because when the router is trying to transmit, this thing is supposed to switch into PA mode. And if you look at the diagram at the bottom, the live setup here, you can see that the other LED is blinking every once in a while. Every time it sweeps, it switches to a PA mode. I can increase the power even more. Let's go from minus 5 to 0, and then we expect even more of the time to be in PA mode. There you go, check it out. Now we can see that we indeed turn the PA on more and more. Of course, we don't expect any changes in S12 because that's in one direction. That's always going to be there. That's when it is operating in LNA mode. But the PA is also turning on more and more, and the light is on even more. Now, unfortunately, this instrument maximum power is 0 dBm. It works up to about 3 dBm. Can enter 3 dB. But as soon as I do that, you can say that it says the generator level is out of range. So it makes it a little bit difficult to use in this kind of test. I would really like to see the ZNL have the power output capability of up to 10 dBm for some strange use cases like this. Now, most of the time, it's not an issue because this instrument has such a huge dynamic range that for measuring passives, even when they have a lot of loss, you would not run into a problem. That's one of the strengths of this instrument, is this huge dynamic range. But now you can see that indeed PA is turned on almost for the entire ISM frequency bands, and then providing actually quite a bit of gain now, about 13 or 14 dB of gain on the transmit side. So that all makes sense. Let's go back to 0 dB. If I go to 0 dB, this error will go away. And now we can try and change the type of measurement we do. We can also look at S11 and S22. And I have added here S11 and S22 as well. You can see these are fairly well matched. Here at the output, we have minus 10 dB. This is not the greatest measurement to rely on, simply because we have an attenuator on one side. So measuring S22, you're really measuring the attenuation at the output, which is quite good. That's why you're getting such a great return. Now on the other side, you have about minus 10. Let me increase the power from minus 10 dBm down to 0, and you can see right away that the behavior changes, and that's expected because the switch is now flipped, allowing you to operate in PA mode. So it's very nice to see all of these features very quickly and easily accessible. This is of course expected from a network analyzer to be able to do all of this. Now there are a few different types of sweeps you can do on this instrument. So if I go under sweep, I can do sweep types of linear frequency, log frequency, CW mode, and time. Now, one of the sweeps that's missing, that should be very easy to implement, or at least I couldn't find it, is a sweep of power. So in this case, a sweep of power would have been very useful. We can fix the frequency, you can put it into CW mode, fix the frequency, let's say at 2.4 gigahertz, and sweep only the power, allowing us to see exactly when the transition point is between the two modes of operation. I would like to see that added to the firmware. At least I couldn't find it, but it's pretty straightforward to do if they wanted to. So if I go into CW mode, for instance, and then I go into frequency, I can change the frequency to a center frequency of, let's say, 2.45 gigahertz. That puts us right in the middle. And you can see we are measuring as a function of points here. So we have 201 points, and you can see the three, of course, the curves that as to be expected. And if I go under power, once again, and if I go to minus 10 dB, you can see that the gain will drastically change over here. Now, if I could sweep the power with the number of points, you would see this curve go up, and eventually it would stay constant and eventually have a step. And that step would be exactly the transition frequency, which is what I was interested to find out. So a couple of these things can really be easily added to the firmware. So let's try another quick experiment here. So here's our S11. I'm placing it on a Smith chart, and I'm measuring this as a function of time. So you can adjust this stop time to whatever value you want to be. It means that you're measuring at a fixed frequency your 4-port S parameters as time passes. So this is very useful if you have some dynamic event that's happening to the circuit and you want to find out how that changes across time. This is exactly where I thought a power sweep would also be very useful, because you can sweep as a function of time. So right now we're setting at minus 10 dBm, and you can see the marker where S11 is, and at 2.45 gigahertz right over here, we have a 50 ohm match and a J29 ohm. That means it is kind of inductive at that frequency. But it's pretty good. It's fairly well matched still. It's about minus 10 dB return loss in this case. But let's see what happens when I increase the power from minus 10 to 0, which means that the PA will be activated, and that's where we saw an improvement in the return loss. So I'm going to go to 0 and press enter. We're going to let it run for 3 seconds, and it's going to readjust. There you go. You can see that now we increased our impedance from 50 to 57 roughly, but we are now less inductive. That actually did improve our return loss, even though the real part of the input impedance went up by about 6 ohms. So all of these analyses are of course possible with a full-fledged network analyzer, and that's what this instrument is. You can do everything you expect from a fairly high-end network analyzer in terms of the mathematical functions you can apply on the traces. But now let's do the exciting part, and let's switch this from a network analyzer mode into a pure spectrum analyzer and see what it can do in that mode of operation. So in order to do some spectrum measurements now using the ZNL, I'm going to reconfigure the setup to allow for a different source to be injected into our device under test. So I'm going to use the microwave switch controller. I'm going to switch that to port 3. So now what we have is, instead of port 1 of the ZNL being connected to the power amplifier, we now have the Rohde & Schwarz SMB V100A connected. And we can configure this to do a whole bunch of fancy modulation or CW or multitone directly into the device under test. Now we don't have to do anything with the ZNL. We're just going to switch it into spectrum analyzer mode. So let's go ahead and change the mode of operation, and I can go under mode button right here. And you can see we have several options here depending on what options are actually available on the unit that you have purchased. And we have a spectrum capability here. So if I click on that, what happens is that it doesn't get rid of the vector network analyzer. It just adds a new tab, which is the spectrum tab. So all the measurement settings that you have are preserved in this tab. If I go back to the VNA, I get the full-fledged VNA exactly where I left it off. This is a really powerful feature. This is one of those things that Rohde & Schwarz pioneered and had this across several of their instruments, allowing you to have multiple tabs with different settings active at the same time and just quickly jump between them. If you go into the multi-view, you can even get all of them at the same time. And whichever one is selected is getting updated. So if I select the spectrum analyzer, the spectrum analyzer begins to update. And you can even adjust this such that it does them sequentially. So it performs a VNA, then it jumps to the frequency sweep, and it jumps to something else if you have multiple tabs. This is really, really great and perfect for an instrument like the ZNL that has many different functions at the same time. So let's go back to the spectrum over here. So right now you can see on the bottom right, I have zoomed into the screen of our synthesizer. We are at 2.4 gigahertz, minus 10 dBm, but nothing is enabled. So of course we see nothing from the spectrum. Let's go ahead and start increasing the power from the synthesizer, which is going at the input of our device under test, and see what happens. Here we go. I'm going to enable it. As soon as I turn this on, we don't see anything yet because the PA is not even active. We're in LNA mode, and the output is connected from the PA side. Let's go ahead and increase that. Here's about -5. We can begin to see some leakage. This is the forward leakage through the PA, even though it's not selected. We can go 4. There you go. We're beginning to see something. So probably one of the two switches in the amplifier is active. This is an interesting measurement. It tells us that one of the switches kicks in before the next one does. You continue a little bit more. There it is now. Both the switches are now active. So I'm going to set this to 0 dBm. Let's come over here and configure a marker. So here's our marker. We can click on this one and say that give me a peak search here, and I can go under search configuration and I can say auto max peak on. So it's basically going to track that frequency for us. There it is. What do we see? We see -12 dBm. We have to add 20 dB to that. So this PA is already putting out about 8 dBm at 2.4 gigahertz. We can push it a little bit further. You can see some other stuff happening over here. It's probably the second harmonic of this. Let's go ahead and increase the amplitude here. What am I looking for? Where's our amplitude? There it is. So instead of 0 dBm, let's go to 20 dBm. You want to make sure that the instrument is protected. So there you go. Of course, the amplitude hasn't changed. It's just that we have now an attenuator kick in. You can see if I go under the RF attenuator, we have a 30 dB attenuation, which is automatically selected by the instrument. So if I click on that, it will make sure that the appropriate attenuation is selected. But our marker is still there. I'm going to go ahead and increase that. Keep an eye on the value of the power coming out at the same time. Let's see how far we can push this. Okay, so we go to 10 dBm. And you can see that we gained 10 dBm more power. So now we are actually sitting at around 18 dBm of output power, which is quite a lot. Let's go a little bit more. Here you go, it is 20 now. So we're sitting at about 7 dBm. That means we have at 27 dBm. Let's see if we can hit 1 watt. There you go, almost 1 watt. There it is. We're just over 1 watt of power. So there's 30 dBm of output power from this power amplifier, which is, of course, its specification. It's supposed to be able to do this. Now, this is a single tone signal, of course, constant envelope. It doesn't tell us much about the behavior of the power amplifier. I want to know what its third order intercept point is and how it behaves across different input power conditions. And you can already see that the power has gone down a little bit, and that's because the amplifier is heating up, being in compression right now. So go ahead and change it a little bit. So I'm going to go over here and make this a little bit larger, and let's create a two-tone signal so we can measure the TOI of this amplifier. So first thing is let's reduce the power. Let's go down to 10 dBm. And let's go into the baseband generator here, into the arbitrary waveform generator. And I've already configured it. Let's go into multi-carrier. So you can see that I have set carrier spacing of 5 megahertz, and I've created 2 carriers. So this is going to be a two-tone signal. If I go under the carrier table here, you can see that we have 2 tones. Both of them are enabled, plus 2.5 and minus 2.5 megahertz around the carrier. So we can go ahead and download that into the instrument, create and load. It's going to do a bit of computation here. There it is. I'm going to go all the way up here and go back. I'm going to go ahead and enable this. There you go, it's enabled. So now the arbitrary waveform generator is enabled, and it should be generating 2 tones. Now we go back onto the instrument here. I'm going to shrink this window again so we can see what we're doing. And let's change some of the settings of the spectrum analyzer. Set the center frequency to 2.4 gigahertz. And let's go ahead and change our span to something a bit more reasonable. Let's say 75 megahertz. There you go. There's our two tones. We can already begin to see it. And we can go ahead and change our span, our resolution bandwidth. Where's our bandwidth? Here we go. Let's see, what do we want? Let's say something like 100 kilohertz. There it is. So we already see a couple of characteristics we were expecting. First of all, here's our main two tones. There's a marker on it. The power is minus 5 dBm plus 20, so it's plus 15 dBm, 2.4 gigahertz. Here are two of our intermodulation products. And the tone in the middle is the carrier leakage from the arbitrary waveform generator combined with the synthesizer, which is actually quite good. Look at the difference between this, and I haven't even calibrated the SMB. It does a very good job already. Now, of course, I expect an instrument like Rohde & Schwarz, with the competition that they have, to have a lot of built-in measurements already into the instrument, and of course this one does. We can do various types of statistical measurements on the signal. We can measure power measurements and emission for pre-compliance, and some of the additional measurements like harmonic distortion and the TOI that I want to do. You can also do measurements on the zero span. Let's go ahead and enable the TOI measurement here. And as soon as you do that, the instrument will automatically detect where the signals of interest are. We have the marker 1 and marker 2. Those are our main two tones. Marker 3 and marker 4 are on intermodulation products. And the power of the main tone is at minus 5 dBm per tone, and the power of the intermodulation is minus 44. So the difference, the IM3, is about 40 dBc or so. And that calculates to a TOI of 14 dBm, which is okay. You have to add 20 dB to that, of course. So you're looking at 34 dBm OIP3 or TOI. So let's go ahead and increase the input signal power and see if this actually improves or not, or it stays constant within the output power of the instrument. I'm going to go ahead and do that. There we go. Oop, that's not what I wanted to do. There you go. Let's increase it. So I'm going to increase it by 10 dB. So we're going to put ourselves into a much higher output power. And you can see now we have a lot more intermodulation terms appearing. That's to be expected as well. But our TOI did improve. We're at about 18 dBm, so 38 dBm TOI, which is not bad. So how does this actually affect the power consumption of the circuit as well? Well, I'm going to readjust that camera so we can see that live. Okay, so here's our setup for measuring the power consumption. And right now, as you can see, it's burning very little power because there is no input. It's in LNA mode. Here we go. You're looking at a power consumption of about 1.3 watts, as it is in standby. Basically, it's in LNA operation. I'm going to increase the power until the PA gets switched in. You should see that coming up any moment. There it is. The PA is turned on now. Now we're burning 5 watts. So maybe part of the PA is indeed getting fully shut down. Let's go to 10. There you go. We can compress it even more. Let's crank it up all the way to as much as it can produce. There we go. That is a lot of intermodulation terms. But look at the power consumption. It's burning 7.8 watts. No wonder it gets so hot under compression mode. But I also want to know what is actually the total power leaving the device right now. Now, one of the things about multiple tones is that if you want to, of course, know the total power, you're going to have to measure and calculate and add them all up, even though most of them are quite different from each other. If you have multiple tones of the same value, you need a power sensor that accumulates all the power and integrates them for you. Now, as I showed you earlier, I already have a power sensor connected to this instrument, so why don't we go ahead and configure it. So let me move this out of the way. If you click on the overview button, this is probably one of my favorite features of Rohde & Schwarz instruments, and they have this across essentially all of their units. It allows you to see exactly what the instrument is doing to the signal flow as it passes through various blocks. They do this for their oscilloscope, network analyzer, spectrum analyzer. This is really helpful and allows you to quickly jump to a particular function as you see it develop over a block diagram like this. So the input right now is an RF port. We can see the power level, offsets, attenuations. We can see the settings of the down converter, 2.4 gigahertz with a 75 megahertz span. The trigger that is used to trigger the measurement, right now it's in free run. The A to D bandwidth, as well as what kind of analysis is being done and what is being displayed. This is amazing. It is, in fact, so good for configuring instruments and getting a bird's eye view that other vendors have copied this and then, to incorporate them into their software as well, because it is so useful. So if we go under input here, we can see that we have, of course, the 50 or 70 ohm here. But if I go under the power sensor, I can enable the power sensor that's connected. I'm going to go ahead and enable the first one, turn it on. Turned on continuous update on, and we're going to say to do a center frequency, but you can also get the frequency coupling, meaning the center frequency of the power sensor, to track the marker. This is useful because these are smart sensors. that the calibration coefficients of the sensor are already downloaded into the instrument as soon as you connect them. So if you change the center frequency or if you change the marker, the correction factors will change with it. This is very useful because there is no uncertainty, there's no error in your power measurements, especially when you want to do very accurate measurements. For us, center is fine. Let's go ahead and close that. Let's go ahead and close this as well. And the measurement shows minus 30 dBm because we haven't configured the microwave switches to reroute the power to the power sensor. It's being rerouted to the input of the spectrum analyzer in this case. So I'm going to go ahead and make that change. I'm going to have to switch to port 2, from port 2 to port 4 here. And there it is, and check it out. As soon as I do that, of course, the signal disappears from the spectrum analyzer because it's being rerouted to the sensor, and we're reading 10.6 dBm. That's the total power. We add 20 to that, we are over 30 dBm, exactly what we were expecting. Now, this is not a constant tone signal. This is a two-tone signal, and it's being integrated across all the frequency. Let me switch it back again so you can see the difference to port 2. There we go. You can see the individual tones are, of course, smaller. You can see the power of the individual tones is not, 10 dBm. That's to be expected because it's doing the integration. So this built-in power sensor into the software is really helpful when you want to make an accurate measurement and calibrate it and do an integrated measurement for broadband signals. And that's why I really thought that that option is a useful one to have on this unit. But hold on a second, I just realized that I forgot to do a measurement I wanted to do while I was doing the VNA measurement. I wanted to know if the power supply has any effect on the switchover point between a PA and LNA. Well, guess what? I can just go back and do that measurement now because it's already up here. I'm going to go to the LNA. It lowers my measurements exactly where I left them off. I'm going to reconfigure the microwave switches to the network analyzer connections. There it is. We're back to exactly where we were. And you're looking at the behavior we saw earlier, where this switchover point right over here was when we switched from LNA to PA mode. Now look at the power at the bottom right here. We're at 12 volt power supply. So I'm going to go ahead and create a marker over here. And let's put our marker exactly at the transition in frequency for that power, which is right over here. And I'm going to go ahead and change the power supply. And let's see if that point changes at all, if it's a function of power supply at all. Okay, I'm going to go ahead and change that. So far I don't see anything. We're at 9 volts already. And it's pretty good actually. Look at that, the gain of the circuit does not change. There's definitely some regulation going on inside, but eventually we should see something. And let's keep going. Continue to go down. Wow, there you go, look at that. You see? The transition point is changing. It's directly a function of the power supply at this very, very end. It means that it must be deriving the reference point for the power detector to detect when power is present. That reference must be driven somehow by some power supply circuitry, and it's derived from that voltage. And when the power supply reaches some extreme level, that transition point indeed becomes a function of the power supply. So now we can go ahead and record that as one of the behavior of this DUT. And look how nice it was to just jump back to the network analyzer measurements on the same instrument. We don't have to change anything. Anyway, so we recorded that now. We can go back and do the up converter measurement we were going to do originally. So now that we tested the entire system using a modulated RF signal, we can now move one step back and use this direct up converter vector modulator chipset, which is fed from INQ inputs from the AFQ100 instead. I can change the setup to use input 4. There you go. And now it's already switched to the other side. So now the LO signal, instead of going this way, it's going into the direct up converter. And we're going to use the GUI from the AFQ100 all the way up there, in order to configure the setup to be able to generate a baseband signal now. So in order to measure the up converter's behavior combined with our PA, of course, we have to provide some baseband signal. So I have already connected the AFQ100, and let me make this a little bit larger. I think it's a little bit fuzzy, but hopefully you can read it. We're going to go ahead and create a two-tone signal in the same way before, except we're going to create it on the upper sideband so that we can see the image rejection of this up converter at the same time. There you go, let's configure that. So you're going to create an arbitrary signal. We're going to use the table sign. So we have a 12 megahertz signal and a 15 megahertz signal that is being generated in I and Q domain, and we're going to generate that into the signal over there. I'm going to turn this on, and we're going to enable it. And there you go. We should see the signal right there. I'm going to make this window a little bit smaller now again, so we can see what we're looking at there. And what do we have? Look at that. That is interesting. So here's our main LO leakage through. here's the image signal, and here's our fundamental signal. First of all, this is of course going through the PA as well, but if I look at this, the signal performance is really not that great. Let me change the marker so that it is doing a peak tracking. Where is our peak? There it is, and do a search and do an auto max over here like before. There it is. So here's the maximum power. We're getting minus 15 dBm, so this is only 5 dBm at the output, which is not that good. But let's go and do a measurement on this. Let's see if this instrument can pick this up. I just picked the wrong thing. Sorry about that. What we wanted was this one. Let's turn all the functions off. And let's go back over here and do a third order instead. There you go. It still picks up the correct tones, even though there are some spurious tones around. So it's fairly clever. Look at that. The TOI is only minus 3 dBm. I'm going to go ahead and increase the IF power and see if we can improve that a little bit. I'm going to go ahead and increase that a bit. What do we have? There you go, increasing it. Nope, that does not help at all. It only gets worse. So what does this tell us? This tells us that we're not taking advantage of the PA at all, that the entire system linearity is limited by our up converter, and without a good up converter, we can never get the kind of TOI we were getting from our PA. But I also see an image signal here. This image signal right over here. I want to know how many degrees of phase offset do I have in this up converter because of this image. Can I eliminate the image completely? Well, I can also do that by playing around with the phase of the IQ signal at the baseband. So let me look ahead and reduce this a little bit. Let's put it over here. So we can go into the impairment portion, and I'm going to turn the impairments on, and I'm going to adjust the phase error and see if we can eliminate that image altogether. That's getting worse. Let's go the other way. Look at that. Almost completely gone. And that's only 3 degrees. Well, 3 degrees is actually a lot. So we have a 3 degree offset. I'm going to make this larger. There you go. Here's our 3 degrees offset. So by applying a 3 degree phase shift between I and Q signal, I'm able to completely eliminate the image, at least bring it within the noise of our measurement. And this is now really, really good image rejection. This is, what is this? 1, 2, 3, 4, about 45, 47 dB image rejection. That's really quite good. So the image rejection is not so much of a problem. Now to eliminate this, we would need to have some DC offset at the input of the IQ modulator to eliminate that. But you can see how being in the spectrum measurement and quickly doing all of this is quite convenient with the ZNL. But I want to push it a step further and take a look and see what happens when we put a modulated signal in, and what happens when we take advantage of the real-time features of this instrument. So let's take a look at an unknown signal. So here's our tone here. It's obviously doing something strange. It's jumping all over the place. There are some minor tones that appear at the bottom over here. It's very difficult to analyze this with a traditional spectrum analyzer. You need some kind of a wide bandwidth real-time analysis capability to be able to decipher what's going on here. Now this instrument obviously has that with up to 40 megahertz analysis. Let's go and enable that. We go under mode, and we go under the IQ analyzer. Now, as soon as I do that, I'm given a graph of magnitude versus time. So we can see that indeed there is something going on, and the amplitude of the signal is changing across time. Now we're looking at a very short time, only 3 microseconds, and it makes it difficult to figure out what's going on. Let's go under data acquisition here. Now under data acquisition, you can adjust the sampling rate, you can adjust the analysis bandwidth. We're looking at 25 megahertz here. But you can also go under the advanced menu, and now it gives you full flexibility on how the FFTs are calculated, how much overlap there is, what the total processing length is. These are pretty handy if you want to capture a rare event, or if you want to figure out how that event is spread across time. We're not going to get into all the advanced functions here. All I want to do is increase the duration that the signal is captured to 5 milliseconds, and the instrument will adjust everything else automatically. Now right off the bat, we can clearly see that there is indeed a repetitive behavior, and the amplitude of the signal is changing over time. But it doesn't look very good because we're not triggering it. Let's go ahead and trigger this. We can trigger an IQ power. Let's trigger on something, let's say minus 25 dBm over here. There you go. So let's take a look and see if we can understand this. Well, first of all, this is obviously an AM modulated signal. We can see this. It has a repetition. It's about 1 kilohertz. So we have a 1 kilohertz AM modulation. But it looks pretty bad because at the bottom, the signal is totally chopped off. Now, by now, we shouldn't be surprised. This is a bidirectional amplifier. When the power is high, it is operating in PA mode. But once the power drops below a certain amount, it switches to LNA mode, and therefore the signal completely disappears, and you get this noise at the bottom. So this is not going to be a very good AM modulation. But at the same time, we can see a couple of other interesting behavior. Look at this point over here versus this point over here. They're not at the same amplitude, meaning that the circuit enters LNA mode at a different power level where it enters PA mode. And that is an interesting hysteresis behavior of this device. It could be intentional, it could be just a consequence of the way the power detectors are implemented. So that's something else to keep in mind. So let's go on the trace here. Let's go on the spectrogram and enable the spectrogram here. And we can see the spectrogram is a very classic type. We have hot spots over here where the signal is high and cold spots when the signal is cold. And we have a history of this spectrogram that's constantly being updated. But it does have a 3D spectrogram, which I really like. In fact, I'm going to make it full screen. There's our 3D spectrogram. And look at it. It's really beautiful. And you can rotate it around. You can see the behavior of the signal, not only across time, but also across frames. So these frames are the historical frames of the signal. Now, in this case, all the frames look the same, and that's because all the frames have exactly the same behavior. This is an AM modulated signal that is the same across time. But if you were to have a glitch in it, you would see that glitch ripple through all the frames. Let me see if I can emulate that by changing, let's say, the amplitude of the signal or something. So let's see if I can turn it on and off. There you go. You can see I'm creating something that's changing, and it's rippling through. There it is. So that's to be expected. But I can also reduce the amplitude of the AM modulation until we get at least a bit of a sinusoidal signal. Let's reduce it. There you go. We're going to keep going down. Let's say 280. There we go. I think I may have to change the trigger level. Let's go ahead over here on the trigger. And let's change the trigger from -25, let's say, to something higher. Let's put it at 0 dBm. There we go, so we don't lose the trigger point. Let's go try again. Reduce the amplitude until we get a nice sinusoid. There it is. That looks pretty sinusoidal. That looks good. So let's see if this is any better. Now, one thing to keep in mind with this spectrogram, especially the 3D one, is that it takes a lot of computation from the instrument. So if you have this and you enable multiple other windows at the same time within the same display, then it's going to be kind of slow. So you really shouldn't look at the 3D spectrogram on its own. You can of course jump back to the other ones, the other measurements. You can even go all the way back to the LNA, to the VNA, no problem. And these tones are because we are injecting a signal, so it's confusing the S parameters. But you can do that without any issues. But if you want to have another window next to this one, you're going to run into some problems. So let's go back onto the trace and spectrogram. And let's turn the spectrogram fully off. So we go back into the magnitude versus time. Well, this looks better. It's not great. It's not very sinusoidal, but it's indeed much better. The circuit is not entering LNA mode anymore. So now that we know it is an AM signal, we can do some more testing on it. Let me just show you what this trace configuration or this looks like here. So if I go over here and if I go under display, I can add other displays to it. So let's look at the IQ vector, for example. Here's our IQ vector measurement here. Let me turn this off. And turn this off as well. So here is magnitude versus time. Here's IQ vector versus time. And if you look over here, this flower shape makes sense. It's because when the amplitude of the signal drops, you go closer to the center. And when it rises, you go outside of the center. So this is supposed to have an overall envelope that is round, which it does. But then as the signal goes down, you get close to the center. So this IQ vector separation is, of course, useful when you're doing IQ analysis. But let's add yet another mode of operation to this instrument. Since we know we're dealing with an AM modulation, why don't we go under mode here and do an analog demodulation window on top of everything else. Look at how many different measurements now we have, which we can, by the way, as always, just jump to whichever one we want. So in this analog demodulation, the very first thing it's looking at is looking at FM. Now we don't want FM, so we're going to go into display here, and we're going to drop an AM spectrum over here. We're going to replace that. So here's our AH spectrum. And we're going to also drop in an AM time domain signal right next to it. There you go. So now we have two displays. Now we're going to configure this a little bit so that it's more suitable to the kind of signal we are looking at. Let's go ahead and change this time signal here. Let's go under sweep. Let's say I want to look at a 5 millisecond signal like before. There it is. Here's our signal. And now that we have it, we can go to trigger, trigger one more time, trigger on AM on 0%. Perfect. Look at that. That looks quite nice now. So here's our AM signal. It's giving us the frequency of the AM signal, which is what we were expecting, about a kilohertz. It's also giving us the THD, which is minus 31 dB, which is not that bad actually. So the signal to noise and distortion ratio we have 35 dB as well. The peak is 77% and an RMS of 54%. That's the depth of the modulation. Now I'm going to increase the depth and see how the THD will suffer as a consequence of it entering into LNA mode. There we go. Let's increase that. Keep an eye on the THD. You can see the THD is getting worse, and as soon as the LNA turns on, look at how much the THD suffers. So right before that, there you go, right off the bat, totally breaks the signal completely. You can continue increasing that, and you can see what happens to the spectrum. All the spectrum on the left side is due to the clipping at the bottom. There you go, we can make it smaller. If I make the AM modulation smaller, the THD should be quite good. Let's do a 30% depth. There it is, and a 30% depth, our THD is a minus 37 dB, which is really quite good. Yeah, so this type of analysis, again, all built into it. I can jump back to the IQ Analyzer again, and you can see the IQ Analyzer. I'm going to have to go into the trigger. And there's a tiny bug over here where you have to change the trigger back and forth each time. I don't think it's triggering right now. Let's trigger at a 4 dBm signal. There you go, there's this. So you can see now the IQ Analysis looks different, of course. Go back to the analog demodulation, we're back to where we were. So switching between all these settings, fantastic. Definitely something that I really enjoy using this instrument for. So we talked a lot about the performance of the PA, but of course the ZNL can also measure noise figure. So I thought maybe we should measure the noise figure of this receiver in LNA mode. So we have a noise source directly connected to the input, which of course with not enough power will always run in LNA mode operation, and the output of that is connected to the ZNL. I've already calibrated the ZNL with this noise source because we do have the 28 volt coming from the special I/O card that's installed on this. So let's take a look and see what the noise figure is. And of course, the ZNL comes with a full-fledged noise figure measurement capability as well. And here is the tab for that. And if you go under Overview, it has the same nice signal flow diagram for noise figure measurements too. It tells you what the instrument is doing during calibration. It tells you what the instrument is doing during measurement. So you can do direct measurement or an offset IF measurement or whatever noise figure you want to do. But the nice thing is if you go under noise source here, because we do have the 28 volt drive, you can mention what kind of noise source you have, whether it's a noise diode or resistor. But if you go under noise smart source here, then you will basically have all the calibration coefficients automatically downloaded into the ZNL if you have that kind of a noise source, just the same way that the power sensor would work the same way, download everything into the instrument. So all of these, I'm just doing a very rough noise figure measurement. I'm assuming a constant ENR. The noise source's ENR is not constant, but that's okay. For our measurements, it's acceptable. And I've already done the calibration, so we're performing a live measurement right now on the LNA. Now, if you look at this, you can see that the gain that this instrument is reporting is very close to the S parameter gain. That's not surprising. It has to match. But every once in a while, you do get a little bit of these glitches that happen in the noise figure. So let's see if it happens here one more time as it is sweeping. You go this time it didn't, but you can see it has some uncertainty. It couldn't do this measurement. You can see there's a dip in the Y factor. So if it figures out that that number doesn't make sense, it doesn't calculate it. Yeah, so there is some strangeness going on around 2.4 gigahertz. Now it was puzzled. I was just first puzzled on where this was coming from. It's not the instrument, this is from the setup. So I'm going to let you think about why you think this is happening, and it's random. Sometimes it's there, sometimes it's not there. So hopefully you can figure that out. So the noise figure is around a few dB, which is what the specification for this LNA is, and the gain matches the S parameter gain, which is what you would expect. So that's really nice to have all of this built into the ZNL. Look at how many diverse set of measurements we did in just this, for this just one component, all using the same instrument. Now I've only really scratch the surface. There is so much more you can do with this. Just a manual of this instrument, it's a couple of thousands of pages with all the different software options that it has, and I recommend that you go take a look at the particular one which you may be interested in. Hopefully you received a good overview of what this instrument is capable of. And there you have it. Here's an extensive review of the Rohde & Schwarz ZNL6. I really like this unit, especially in automated environments, because it can do so much in the same form factor. There are some minor improvements that can be made to it, which I'm sure Rohde & Schwarz will do in the future. As always, if you like this video and this review, please let the manufacturer know. I don't get any sales or any revenue from this instrument, of course, but it allows me to have a good relationship with them and bring you state-of-the-art instruments in the future for teardown and reviews. As always, I'll see you in the comment section.